Next talk is, so this is close to my heart. I went to grad school at the University of Oklahoma and was, you know, physics and astronomy there, old school building. It's brand new now. It's really nice. But I was always jealous of the people up at the National Severe Storm Labs. They were the slickest outfit on campus. They had the best computers, everything. And one of my outside advisors was from the meteorology department. So it's constant jealousy. And of course, they did something incredibly important for us. Anybody who lives in Norman for a few years, you will run into severe storms many, many times. So great pleasure to have Corey speak here and tell us about what they're doing in terms of the real-time decision making in this field.
Hopefully by the end of this talk, all of you will be equally envious of me and the work I do. Yeah, this work is taking place within the NOAA Warn-On Forecast program. So the goal there is to produce thunderstorm scale ensemble model prediction forecasts in real time. I work within the Cooperative Institute for Mesoscale Meteorological Studies and National Severe Storms Lab. The Cooperative Institute is partnered with the lab and with the University of Oklahoma. So in this talk, I'll first introduce you to Warn-On forecasts, why we need it, what the goals are, followed by an introduction to numerical weather prediction of thunderstorms, which is at the heart of Warn-On forecasts. Then talk about an experimental real-time Warn-On forecast system that we've been evaluating each spring, followed by some notes about some of the major challenges that we're facing in Warn-On forecasts, namely a physical science challenge, which is the fact that thunderstorms inherently have limited predictability. And of course, some of our own practical limitations enhance that lack of predictability. Computational challenges posed by this task of processing this massive ensemble output in real time and also interpreting the output in real time. The human factors challenge of actually tailoring this output to forecasters who are operating in a very time-constrained environment and having to act on this output in a matter of seconds or minutes. Okay, so first to provide some context, people in this room and at home are probably most familiar with kind of the next day type of thunderstorm forecasting. Many of you have probably seen the Storm Prediction Center or SPC outlooks. And by the way, in meteorology, we have many, many acronyms. We like to think that we have more acronyms than other scientific fields. I don't know if it's actually true, but there are a lot of them. Anyway, so here's an example of some SPC outlooks. These now go out to 8 days. So here's an example of a day 6 outlook going down to day 2 and day 1. And as we get closer to the event, there's more specificity as we become more confident. So these are fairly long range. Then as we get closer in time to the event, the SPC will issue the watches such as tornado watches, severe thunderstorm watches. These are typically several hours before the event and are about the size of a state now. And then when an event is imminent, that's when the local National Weather Service weather forecast offices issue warnings. And these are on the scale of a county and are typically issued tens of minutes to maybe an hour in advance, depending on what kind of phenomenon is being forecast. Warn-On forecast kind of resides down here. We're focused on the 0 to 3 hour time range. But backing up for a moment, most people, including meteorologists that are working at these spatial scales, they think in terms of forecasting out to maybe 12 to 36 hours. And that's where most storm scale NWP, numerical weather prediction, is happening right now. Now, when you're looking that far out, you're asking very different questions than you are when you're looking at an event that's going to happen within the next few hours. You may be asking questions like, around where and when will storms start and end? What will the storm types be? And related to that, what are the general hazards from these storms? Is this more of a tornado day? Is this a hail day? Flash flooding? How widespread are the storms going to be? What will their general motion be? But once you get down to Warn-On forecast scales, now we're asking much more targeted questions. where will this particular storm that already exists go? How fast will it move? And how exactly will its risks evolve? And ultimately, we want to be able to produce probabilistic guidance that looks something like this. So for an individual storm, probabilistically, how will the tornado, flash flooding, large hail, and damaging straight line wind risks evolve over the next few hours? So one problem we're attempting to address is the gap in guidance between the watch scale, spatial and temporal scales, and the warning scale. And it's clear why this gap in guidance currently exists. Watches are currently largely informed by NWP model guidance that's issued up to 8 hours in advance, forecasts that go out 3 to 12 hours. And we have plenty of guidance at those forecast lead times. And also that on these scales, like on the scale of a state, the environment, the larger scale environment that the storms are going to evolve in already tells you a lot about what to expect. And so expert forecasters could actually do pretty well without NWP guidance, although the NWP guidance has proven to add significant additional value. Now, once you get down to the warning scales, currently there is no operational real-time NWP guidance at these very short lead times. And so forecasters in the best case are reliant on their own experience and the latest radar imagery that's available. In the worst case scenario, a storm chaser or spotter calls in a tornado report and then a warning is issued. But of course, that's very suboptimal.
Court, what, in terms of what you would like to get done the best in predictions, is it flooding? Is it wind? Is it both? Are they weighed differently?
The way that warning forecast is typically pitched, we focus on tornadoes. And that's partly because a lot of the highest profile events are tornadoes. And there are cases where if we could get that tornado warning out 30 minutes in advance, then, and I'll get into this more a bit later, then we could warn managers, people in charge of evacuating stadiums or hospitals or schools that there is an impending threat. And so there will be some scenarios where many lives could be saved that way. But we're also very concerned about other hazards too. Tornadoes were the obvious first hazard to tackle, but people within the group are also now hitting flash flooding pretty hard. Flash floods often, with some tornado events, actually kill more people than the tornadoes themselves.
I was going to say they were much more disturbing in terms of affecting a larger number of people than tornadoes were, which are a very focused type of event. So I just wanted to know how it was weighed. Tornadoes, of course, are sexy. So
yeah, they really are. Yeah, I would say flash flooding and tornadoes are receiving the greatest attention right now. Straight line winds are just harder to forecast. It's not clear yet how to best utilize the storm scale NWP guidance for that. And similarly for hail, hail and wind are probably the lower priorities right now, but ultimately they're all important.
A little more detail. Same lines. Do you, in terms of your target audience, say, do you distinguish between hazard to life versus damage to property at this level, or is that aggregated? Do you have different populations?
Certainly different.
Civilians versus working population.
So with these warnings, we're not really. The warnings will contain text saying, the kind of standard text saying, that this poses a risk to life or property. It's not clear yet how we're going to tailor the ultimate output of warn on forecast systems to the public. Likely, we will divide the public into at least two categories. Lay people, it's not clear yet whether they could take appropriate action on the probabilistic information that we'll be issuing. And I'll get into this more in a moment, but right now warnings are deterministic. You're in the warning or you're not. we want to go to a probabilistic, and this is actually part of a much larger framework called facets, where we're trying to get to away from the deterministic paradigm, or we want to supplement the deterministic paradigm. There would still likely be deterministic watches and warnings, but complemented with probabilistic guidance. Whether lay people could make effective use of that guidance is unclear right now, and that's why we need social scientists to look at those issues and see whether it would do more harm than good to make that guidance available to the general public. But certainly for the types of people I mentioned earlier, for people in charge of schools and so forth, they would definitely be a target of this probabilistic guidance. Now, whether there's any way to kind of actually separate the two in this day and age, inevitably some of that probabilistic information would leak out, through some channels to the general public. But yeah, so we're very mindful of the fact that the general public is not this uniform category. There's many important subdivisions within that broader category that need to be treated differently. Okay, so getting back to this gap between the watch and warning scales. So again, deterministic, probabilistic. So here, this is an example of the type of forecast that could be issued based on Warn-on forecast ensemble output, where you have probabilities of severe weather occurring. So this is an example of a forecast that actually would have done pretty well, where the storm reports indicated by these dots tend to be concentrated in the areas of the higher probabilities. So that's what we would like to see. So the ultimate outcome of these Warn-on forecast systems ideally will be that the Weather Service is enabled to issue probabilistic warnings earlier than the current deterministic warnings, and therefore provide advance notice to the groups I mentioned before. So here's the Warn-on forecast paradigm. Here we have an example of a developing thunderstorm. It's too young to give any clear indications of whether or not it's going to produce a tornado, for example. But then the Warn-on forecast ensemble would produce this probabilistic forecast, in this case, the probability of a tornado occurring at each location. And then ideally, the storm would tend to evolve and then produce a tornado generally where the forecast probabilities are highest. Okay, so this all hinges again on these storm scale or convection-allowing numerical weather prediction models. So these are models with sufficient resolution to simulate and predict storms reasonably well. And we found through experience that 4 kilometers is about as large a horizontal grid spacing that we can get away with to do this. And that's mainly at longer lead times. Once we start looking at Warn-on forecast scales, we're really looking at 3 kilometers or less. Now, of course, that's still very coarse resolution relative to the processes that need to be simulated. So there are many physical processes that must be parameterized, including cloud microphysics, subgrid scale mixing, and these contain large errors, and I'll get more into that in a few slides. The current state-of-the-art operational CAM we have is the High Resolution Rapid Refresh, or HRRR. This is run on a 3-kilometer grid every hour, and here's an example of output from the HRRR. If you're familiar with radar imagery, like you would see on the news, this might look like a radar composite to you, and indeed it does, but this is actually a model forecast, just illustrating that these models are capable of producing fields that are quasi-realistic. Now, of course, there's a difference between producing realistic fields and producing fields that are accurate, that actually match observations in a given case. But certainly, this kind of realism is a necessary, even if not sufficient, condition to produce accurate storm scale forecasts. But yes, these forecasts have very large errors for a number of reasons. First, storms have inherently limited predictability. In other words, perturbations grow nonlinearly. So any errors within the initial conditions or arising because of limitations of the model will grow rapidly. Forecast initial conditions suffer large uncertainty and bias, largely because even with all our instruments nowadays, even with GOES 16, a small portion of the atmospheric state is actually observed, a very small percentage. Furthermore, these observations have instrument errors, representativeness errors especially. Model errors are often very large at these small spatial and temporal scales. This is in part because of the computational constraints on model resolution, numerics, and the physics parameterizations, but also because we have limited knowledge of the processes that we're trying to parameterize. So even if miraculously we could suddenly there were no computational constraints, we could use arbitrarily, we weren't limited in that way, we still would not be able to parameterize these processes very well. So part of the solution to this, it's a necessary piece of the solution, is to use ensembles of CAMs and not just deterministic single forecasts. So these are groups of CAM forecasts with different initial conditions and optionally also different physics parameterizations and even dynamical cores. And by dynamical core, I mean the governing equations of the model, the numerics used to integrate the equations, and also the model grid itself. Because with NWP models, the atmospheric state variables are typically not all co-located at the centers of grid cells. Actually, there's different options. You could have these variables here and these variables there. So that's another choice that has to be made in the design of the model. And each has strengths and weaknesses. So anyway, so you can vary the physics parameterizations and even the dynamical cores in these ensembles. So this accounts for the uncertainty in the model. The different initial conditions accounts for the uncertainty in the initial condition. And so ideally, the ensemble forecast then provides a representative sampling of the probability distribution function of the future atmospheric state. In practice, that's certainly not always the case. So how do we initialize these ensembles? Well, this is done via data assimilation, where we optimally blend the latest available observations with background fields or first guess fields that are provided by the latest model forecasts. So the types of observations we assimilate include surface and upper air observations that are provided, for example, by aircraft or balloon-borne soundings, and optionally radar and satellite data. For war-on forecast, radar data is a necessity, and satellite data has also been shown to improve things significantly. In order to do the assimilation, we require background error covariance estimates that relate observations to the model state variables. So in other words, for example, if you want to assimilate a temperature at a given location, that's all well and good, but you also want to know how assimilating that temperature should update the temperature at the surrounding grid points and also the other state variables at surrounding grid points. And this, again, is because we're only observing a very small percentage of the atmosphere. So there are two main flavors of data assimilation in use in storm-scale NWP. There's variational data assimilation, which is just deterministic. And these use constant background error covariances. So in other words, regardless of what the current state of the atmosphere is, you're assuming the same background error covariance, which is clearly suboptimal. Ensemble common filters, on the other hand, provide flow-dependent background error covariances. And they do so by virtue of using an ensemble of forecasts from which you can actually estimate those background error covariances. Modern CAM DA systems tend to use either the ensemble common filter alone or a hybrid ensemble common filter variational framework. But either way, there has to be some accounting for the flow dependence of these background error covariances. OK, so now getting into this experimental Warn-on forecast system called NUSI. This is a weather-adaptive, real-time CAM ensemble that targets the region of greatest severe weather risk on a given day. It's frequently updating, with data assimilation occurring every 15 minutes and forecasts being issued every 30 minutes. It comprises 36 members, which is probably a bit on the low end, but again, we're computationally limited. And then only 18 of those members are used for forecasts, although we found that smaller ensembles are needed for accurate forecasts than for the data assimilation itself. And as I'll show, actually, the NUSI has performed, I think, remarkably well. We're not doing too bad. Physics diversity is used, again, to account for the uncertainty in these parameterization schemes. And the NUSI is evaluated every spring in the NOAA hazardous weather testbed that I'll describe a little later on by scientists and forecasters. And this is actually a really important interdisciplinary effort that is absolutely critical to testing and evaluating the latest experimental storm scale numerical weather prediction products. Okay, so each day that the NUSI is run in the spring, forecasters look at the Storm Prediction Center outlook for that day. And, well, I say forecasters, but I mean members of our team that are actually running this experimental ensemble. They look at the latest convective outlook, and based on that, nest a domain typically of about this size, and that's the domain within which the ensemble forecasts are made. We can't just run over the entire US again because of computational constraints. So each day, and this will change over time, but this is the latest configuration as of last spring, the NUSI is initialized at 18Z, or about 1 p.m. Oklahoma time, with what I haven't talked about, it's the HRRR. It's the ensemble version of the HRRR that I introduced earlier. That provides the background forecast within which observations are assimilated at this first assimilation time. And then after that, every 15 minutes, the latest observations are assimilated. And then after each analysis update, the ensemble is integrated 15 minutes forward in order to provide the background for the next analysis cycle, and so on all the way through late evening. And then every 30 minutes, either a 90-minute or a 3-hour forecast is generated. And again, that's done using 18 ensemble members. So it's 18 individual forecasts within that green domain I just showed. So here's an example of what these ensemble forecasts look like. So beginning on the left, this is a forecast from a single ensemble member. So thinking deterministically here. The color shading is reflectivity, or a measure of precipitation intensity. And the gray shading is a measure of rotation, which tends to correlate with how severe a storm is, including how likely it is to produce a tornado. Here's a paintball plot in the middle, showing now all ensemble members with different colors of shading, showing the rotation tracks from each of the ensemble members. So now we're getting a feel for the fact that this is an ensemble product. And then on the right, we have probabilities that are calculated from these ensembles of rotation tracks. So now we're looking at the probability of rotation exceeding a certain threshold at each grid point over the course of the forecast. So this is the kind of output that ultimately forecasters will see. Okay, so as I mentioned before, storm scale predictability is quite limited. We're also computationally limited. So how can we optimize the ensemble design such that we optimize the trade-offs that we're forced to make? For example, we can't have arbitrarily large ensembles or arbitrarily fine model resolution. But it's not clear a priori how to optimize that trade-off. So how do we determine what the optimal trade-off is? Well, one way is to construct idealized sensitivity experiments that allow the experimenter to isolate and systematically explore the forecast errors that arise from different sources, such as limited grid spacing or limited ensemble size. The drawback, of course, being that we don't know what the real-world model errors are, and so we can't really account for those in these types of experiments. So it's hard to say how immediately those results can be extrapolated to real-world prediction systems. On the other hand, we can compare real-world forecasts, such as those generated by the NUSI, run using different configurations. So now we're accounting for real-world model errors. The drawback there, though, is that it's then difficult to verify due to lack of observations. and isolate impacts of individual error sources. Because now we actually have a convolution of different error sources. We can't isolate the impact of any one error source. So there are trade-offs between both of these experimental frameworks. So I think it's critical to perform both types of experiments. And in some cases, it's possible to construct experiments that leverage the strengths of both, and I'll provide an example of that in a moment. We've also begun using machine learning to try to identify forecast biases and sensitivities in real-world output. So this is a way to hopefully improve the forecasts without having to improve the models, the physics parameterization schemes, because that's very difficult, and it may be a while until we can make substantial progress in that regard, although it's still critically important ultimately. So here's an example of an idealized experiment designed to look at the impact of a particular type of forecast error. In this work, we looked at the sensitivity of forecasts to the radar storm geometry. So by that I mean, so here, this is a framework where radar data were assimilated, and the question was, how much does it matter if the radars are far away from the storm, at which point your observations are becoming very coarse in the area of interest? And how much does it matter if the radars are collinear with respect to the storm, in which case you're not getting very independent information from each of the radars? So to explore this, we used observing system simulation experiments where we simulated 3 different supercells within 3 different storm environments, generated pseudo-radar observations from those simulations, and then assimilated them with an ensemble common filter, and then used the resulting ensemble analysis to initialize an ensemble forecast. And within these experiments, we fixed one radar at greater than 100 kilometers from the storm, and repositioned the second radar in order to affect different radar storm distances and angles between the radar beams. And I should mention that in addition to measuring reflectivity, as I showed earlier, Doppler radars measure velocity in storms, but only in the direction of the radar beam. So only one direction of the 3D wind vector field. And so the narrower this crossbeam angle becomes, the less useful, again, the less independent the Doppler velocities from the 2 radars are. So the question again was, will the frequently poor radar storm geometry that occurs within our radar network fundamentally limit warn-on forecasts? Will we just not be able to get very good forecasts because of these observational limitations? And it turned out the answer was no. Even in cases where we had very poor crossbeam angles and both radars were really far away, we got pretty decent forecasts. So these are plots of low-level rotation, red being truth, and the shading being probabilities of low-level rotation exceeding a threshold. So ideally, you would like to see the hotter colors primarily confined within these red contours. And this would actually be a great forecast considering what our current forecast skill is. And this was in the worst scenario that was tested. So we discounted that as a major source of forecast error. We next looked at the sensitivity of forecasts to the model grid spacing. So we simply ran simulations that were identical, except the horizontal grid spacing was varied from 333 meters, which is far beyond what we can run in real time currently, all the way to 4 kilometers. So these are showing the reflectivity fields after 2 hours, so 2 hours into the future, 1 kilometer above the ground. And if you compare, for example, the 2 and 3 kilometer results to the 333 meter or truth results, you see they're pretty similar. Once you get to 4 kilometers, in some cases, you get dramatic degradation. And that's why I said earlier that I think 3 kilometers is kind of the upper limit model resolution or model grid spacing that we should be using in warn-on forecast. We also looked at sensitivity to the initial condition resolution. So in other words, what grid spacing do we need to use for the data assimilation? And what are the observational requirements? If we simply don't have observations at very fine resolution, are we doomed from the start? Now this is an example of a hybrid real data / idealized experimental framework that I spoke of earlier. Here we took single member analyses from newsy analyses of a real supercell thunderstorm. Supercells are the types of storms that tend to produce most of the significant severe weather in the US. We took one of those real supercell analyses and downscaled it to about a 300-meter grid. And then generated similar analyses, except that they were spatially filtered with cutoff wavelengths that range from 2 to 16 kilometers. So with these 16-kilometer cutoffs, and even the 8-kilometer cutoff, we're smoothing the initial condition quite a bit. And we add noise to these initial conditions in order to generate ensembles. And I don't have time to go into it, but it turns out this is critical for identifying systematic impacts of initial condition resolution and other error sources in storms. We then integrated the original and the spatially filtered initial conditions out to 2 hours and then compared the forecasts. So these were idealized experiments in the sense that we know what truth is, and so we had full control over what errors were involved. We isolated the error just to the initial condition resolution. But we also initialized from an analysis of a real case, and we used the same model and physics as the newsy did. So we're representing all of the physics, all the processes that are represented in real-world numerical weather prediction models, and also initializing from an observationally constrained analysis of a real event. So this should add realism to the experiment. And what we found was surprising insensitivity to the initial condition resolution. So for example, if you compare, and this is for 3 different cases again, if you compare the 8-kilometer panels to the control, you see that not a lot of difference. So whether you had a very fine initial condition or a significantly smoother initial condition didn't make much of a difference out to 2 hours. Once you increase the cutoff wavelength applied to the initial condition to 16 kilometers, well, now in at least one case you see some bigger differences. And due to time, I'll just say that most recently we've looked at the sensitivity of forecast spread to the initial condition spread. How much is gained? How much is the uncertainty in the forecast reduced by reducing the initial condition uncertainty? How much can we expect our forecast uncertainty to be reduced in the future as we simulate more observations, different types of observations, and therefore better constrain that initial condition uncertainty? And another very recent activity has been using machine learning to post-process the Warnod forecast output. So this has been done in 2 ways. First, to facilitate evaluation of the newsy system performance, and also to provide an automated and ideally a reliable way to correct model biases in the ensemble statistics. But it remains to be seen whether we have a large enough training data set to actually do that effectively. So beginning with the first one, a colleague looked at the relative impact of different features on the quality of forecasts as measured by the number of matches and the number of false alarms. So this was an object-based rotation track evaluation framework performed in both all of the, so using the full data set that was available, and then restricting to cases characterized by a certain type of environment that's kind of unique to the southeastern United States, and that's been getting a lot of attention recently. Okay, and this was using a random forest technique. So through this machine learning, he found that the 2 atmospheric variables that best distinguished between matches and false alarms, or speaking over generally good and bad forecasts, were these 2 variables, which I won't get into right now. But just, again, this is just to kind of illustrate some of the machine learning applications that are beginning to be performed within storm scale meteorology. This is very new work, applying machine learning to correct the raw ensemble output from ensemble prediction systems. So on the top, we have the raw probabilistic ensemble output with the black contours being the verifications. So ideally, we would see the hotter colors within the black contours. So you see that in this case, the raw ensemble misses a lot of the rotation tracks. Now, when a random forest is trained on many previous cases and then applied to this case as part of a leave one out cross-validation exercise, we see that the probability of capturing these rotation track objects increases quite a bit, but we also have a high false alarm rate. So it's not clear whether we're actually getting a better forecast now by virtue of post-processing statistically the dynamical output that comes out of the NUSI ensemble. But this is work in progress. Again, this is just to illustrate one of the machine learning applications that we've started using. So our real-time computational challenges are not peta to exascale like some of the other groups that have been represented here, but it still poses a pretty stiff challenge. Every 15 minutes, the ensemble of 36 members is updated on the order of 10,000 observations and then integrated to the next cycle. Every 30 minutes again, 18 members are integrated forward for 1.5 or 3 hours. There are about 3.5 million grid points and on the order of a dozen state variables at each grid point. The forecast output is stored every 5 minutes, so that's 8, 18, or 36 output times per forecast. Each forecast must then be post-processed into over 100 probabilistic products and then uploaded to a website that can be accessed by forecasters, all within about 30 minutes of the forecast being initialized. So there are about 7,500 images that are generated per forecast and uploaded to the website. As I'll speak about more, these products are designed to convey useful information over the entire forecast period to forecasters in less than 30 seconds. So basically, we're taking a vast amount of ensemble output data and trying to distill it into something that forecasters can make sense of in seconds to perhaps minutes. So this produces about 1.2 terabytes of data per day. I know that seems laughably small compared to what others have talked about the last few days. But I/O is a major bottleneck for us. I'd be happy to hear suggestions about how to reduce that. But I know at least when I was more involved in this part of it, the I/O sometimes was taking up to half of the total wall clock time for the running of this ensemble system. So we run this on a Cray machine. We're very lucky to have it. It's reserved entirely for Warren forecast research and then running this NUSI experimental system in the spring. It has over 4,000 Ivy Bridge cores, and about 3,000 of those are used by the NUSI. We use several types of parallelization. First of all, the ensemble member forecasts all run simultaneously. That would be impossible if we didn't have this many cores to use. We use MPI, more specifically, the domain of each forecast is tiled up so that they can be processed independently or in parallel and then stitched back together at the end. And this Cray has a Lustre parallel file system which accelerates the I/O. It's very easy for us to generate hundreds of terabytes of storage, both through the NUSI and then the experimental work, the non-real-time retrospective experimental work going on in the group. So storage reduction is becoming a bigger and bigger issue. So to tackle that, we use NetCDF4 compression. That's a lossless compression. I don't know if you're familiar with NetCDF4. That's a file format that was developed by meteorologists and is in very common usage within the atmospheric science community. We also apply some lossy compression after the fact when we start running out of disk space. And I think when we compress, we typically retain about 16 bits of information, and that's sufficient for our purposes. Here's the NUSI website I mentioned before. So this is the sort of thing that a forecaster would see and that you can see if you want. I'll provide the link in a moment. So this is the culmination of a long period of interactions with NWS forecasters and participants in the NOAA hazardous weather testbed, which I'll talk about more in a moment. And being in the same building as the Norman NWS Weather Forecast Office has been a big boon for this. We researchers, we don't know what the forecasters, want to see in the forecast. We don't know how the forecasters utilize information. We can look at a forecast and think, oh wow, that's totally useless, but a forecaster may be able to glean very useful information from that forecast. So we have some very experienced forecasters to work with within our building, so that's been very helpful for this and other efforts. We've actually brought in a computer scientist to help revamp this website. And it's sophisticated enough that now we're looking toward developing video tutorials and pop-up help images and notes to actually assist forecasters and other users in interpreting the output. So this website provides the real-time guidance generated by the NUSI during the spring. So you can actually go to this URL and find all the output from the last 2 springs, and that will again be active in 2018. So finally, more on the NOAA hazardous weather testbed pictured here. This is a space that brings together the research and operational communities, which is critical because, again, researchers don't know a priori what the forecasters' needs are. The forecasters are not always aware of the latest developments of, within storm scale, numerical weather prediction, and other applications. So this has been going on now for, I think, almost 20 years and has been tremendously helpful. And it consists of, again, testing cutting-edge products. Can the forecasters make use of these? How can they be better tailored to the needs of the forecasters and so forth? So lots of interdisciplinary research takes place. For example, people may guide participants through simulated real-time experiments where they work a case as if it's in real time and they issue warnings and so forth. And, and we can see how they actually make use of some of these cutting edge tools. And I'm not directly involved with any of this, but one of the things I find the most interesting is, the use of eye tracking software to actually, see, where the forecasters are looking on the screen most of the time, and that helps track, what kind of products they're making use of. So the NUSI has been tested extensively in the HWT spring forecast experiment in a number of ways, and it's really this multi-method approach that's critical to actually providing an overall holistic assessment of how forecasters use the data, which again is not always intuitive. So this can be broken up into 3 categories: pseudo-operational testing, which is retrospective evaluation of NUSI forecasts and derived experimental forecasts. Real-time operational testing, where members of the Warn Forecast team work in real time with forecasters to try to get them to use the NUSI output in their decision-making process, and then learn how they're actually using the output. And survey work, where we try to gain a better understanding of how well meteorologists interpret the probabilistic information that is coming out of the NUSI system. So dealing with the first one, pseudo-operational testing, we've explored how short-term ensemble forecast guidance from the NUSI can be used by an expert forecaster who's actually semi-retired, probably with 30 or 40 years of experience, really high-quality forecaster. And spring forecast experiment participants to produce 1-hour severe weather probabilistic outlooks. So here's the NUSI ensemble output now generate a probabilistic forecast, and then the next day we'll see how well those forecasts did. So this allows us to observe how forecasters' understanding, use, and attitudes about NUSI guidance evolves during the experiment, and I'll have an example of that in a moment. Here's one of the surveys that are given to the daily spring forecast experiment. Participants, like some of the questions may be, what severe weather threats do you believe are the most likely based on the NUSI guidance, and during what hours? Let's see, how confident are you in today's outlook? What products were the most helpful in today's forecast? What NUSI products, and so forth. So here's an example of, so here is a chart of how the expert forecaster that I referred to earlier, how their product usage varied. Well, let's see with this one first. This is showing how their use of deterministic versus ensemble products evolved with time. So again, deterministic being the more traditional framework. So not surprisingly, they in the beginning, they were more reliant on the deterministic products that had always been available. But as time went on and they learned to trust and value the NUSI output, the probabilistic output, they began making much greater use of it. And that's what we wanted to see. And we were further able to see what kinds of products they were spending the most time examining. And that was actually done by recording the forecaster's screen and then after the fact, actually looking at where they tended to spend their most time.
I was just wondering, what do the stars and crosses on the lower graph mean?
Let's see, can I remember this? It's not tremendously important, I know that. Yeah, I can't quite remember because it was a pretty technical detail that doesn't really alter the interpretation of this plot. Sorry, I can't give a more complete answer than that. Again, this is definitely outside of my wheelhouse. And so the expert forecaster was also surveyed daily, on the use of the NUSI output. And here are some examples of things that he said. On most days, NUSI was exceptional at identifying which storms had the greatest potential to become severe. NUSI is a big help in forecasting storm evolution. So it's this kind of feedback from forecasters that we really rely on to have an idea of how useful is this guidance. And here are examples of the 1 hour forecast that participants were asked to issue. So on the right here is the verification. This is this would have been a practically perfect forecast. You see the storm reports are nestled within the highest probabilities. Here's the forecast that was issued 3 hours before or 2 hours before the event, and pretty decent forecast. And then the forecast improved the next hour as we got closer to the event. So this was a desirable outcome. But again, just to give you an idea of the kinds of evaluations that are going on within the test bed. Here is a success story from the use of NUSI in real-time NWS operations. This is the Elk City, Oklahoma tornado that occurred. This was an EF2 tornado, $25 million in damage, 1 fatality, 10 injured. Here's some of the output from the NUSI for this event. So the star is close to where the tornado occurred. And the Weather Service was actually able to take action on this guidance and incorporate some unusually specific wording into their tornado warning. Namely, there is a high probability that tornado warnings will be issued. You never really see that wording. It's, the tornado warning is issued or it's not. So they were able to use that guidance and provide a bit more detail than they otherwise would have been able to. And as the forecasters become more comfortable with the use of NUSI guidance, then hopefully this will become a more common occurrence. Finally, interpretations of the NUSI products. How well do meteorologists interpret probabilities? So, aside even from the general public, well, what about the forecasters themselves? So, testbed experiments were given this survey to complete. So it wasn't just researchers, or it wasn't just forecasters, but also researchers and some students and postdocs. And they were asked questions like, given this graphic, which is probability of accumulated rainfall greater than 0.01 inches, interpret this graphic. And we got a variety of responses. And in this case, most of them were correct. People tended to have a pretty good idea of what this actually means. Not all, though. One person said, oh, this is a heavy rain event. In actuality, we don't know. This is just the probability of minimal rainfall occurring. We asked about percentiles. In an ensemble-based probabilistic forecast, what do you think the 70th percentile value of accumulated rainfall presents? Of the 60 participants, just over half had a clear understanding of what percentiles are. So just under half actually demonstrated misunderstanding. For example, the accumulated rainfall amount that 70% of the members are producing. Nope, that's not right. Accumulated rainfall that at least, regions shaded represent the union of at least 70% of ensemble members. Nope, that's not what it means. So we have a task ahead of us, actually training forecasters to make use of this output. When even the scientists actually didn't do a great job of interpreting, of actually knowing what a percentile is.
Of course, grad students were the best.
Yeah.
What's that?
The grad students were the best.
Oh yeah, I hadn't really noticed that. Well, it's a low sample size, but yeah. All right, so in summary, the NOAA Warn on Forecast program is developing NWP ensemble prediction systems that will ultimately enable forecasters to issue tornado, severe thunderstorm, and flash flood warnings further in advance and with greater accuracy, and hopefully lower false alarms. A prototype real-time Warn on Forecast system is being evaluated every spring by operational forecasters and research scientists. This new Z provides valuable probabilistic forecast guidance for severe thunderstorms at 0 to 3 hour forecast lead times. But the limited predictability of storms and the massive data volume of storm scale ensembles pose major scientific, computational, and human factors challenges. So ongoing challenges include the need to continue refining knowledge of the impact of different forecast error sources in order to better prioritize improvements to the ensemble configuration, and to refine knowledge of how forecasters actually use the ensemble output in order to better design these Warn on Forecast products, and also to design forecaster training modules, for example. We need to improve our ability to anticipate forecast skill for individual events and storms. For example, given our knowledge of the current storm environment, would we expect there to be a higher or lower confidence in the forecast on a given day? Since the ensemble spread may not always accurately capture that. We need to continue to develop machine learning techniques for calibrating forecast probabilities, largely again to account for the biases in the model physics. Ultimately, again, we're running at 3 kilometers right now. Ultimately, we're going to need to scale to tens of thousands of CPU cores in order to achieve model grid spacings of 1 kilometer or less. That's been shown to be especially important for tornado prediction, which isn't surprising because tornadoes tend to be on the order of 100 meters in diameter. So likewise, the real-time post-processing, generating all those probabilistic images, uploading to the website, that will also need to accelerate. We need to improve the physics parameterizations, errors in which greatly limit storm scale predictability, but that's a pretty tall order. I didn't talk a lot about it, but verification is a major challenge at these scales. First of all, we have a lack of observations, so in many cases we don't have ground truth. Furthermore, even when we do, even when we're verifying against observations that we actually have, it's hard to design objective error metrics that are actually consistent with our subjective interpretations of the quality of the forecast. Traditional metrics just oftentimes fail miserably. The objective metric says, this is a bad forecast. Your eyes say this was a great forecast. How do we design objective metrics that are consistent with our subjective impressions? And object-based approaches are clearly a key to that, but but it's not so simple as that. So I'd like to acknowledge the rest of the Warn on Forecast team. There's a list of references here. Notice it was mentioned this morning, about in high energy physics, papers oftentimes have more co-authors than words in the paper itself. Clearly not the case in meteorology. There's 2 authors, but anyway, I'm happy to take any questions.
Questions from the audience?
So in case you announce a pre-warning so that there might be an actual warning afterwards, what is the action that you expect people to take in that case?
We don't know. So fortunately, social science has rapidly become a much greater priority in meteorology to explore questions like that. What should we expect people to do with this information? Because us physical scientists, we don't know. We might know what we would do. We're not representative of the larger population. So, but answering those types of questions is critically important. The forecast could be perfect, but if we can't get the public to react in a desirable way, it's ultimately useless.
Instead of an ensemble of multiple deterministic models, is there any prospect of actually building measures of uncertainty into a probabilistic, single probabilistic model?
I don't know if this gets to what you're asking, but we do have ensembles that consist of where each ensemble member uses the same model, except that there's some sort of stochasticity built into the physics parameterization. So either the empirical constants used by the schemes are randomized, or there's something that's called a stochastic kinetic energy backscatter technique that also, it's a way of introducing noise in order to account for uncertainty in the physics scheme.
It seems like, some of the uncertainties are quantifiable. I mean, you spoke of initial condition uncertainty, and other elements of the physics are, you actually have a reasonable estimate of where it is, and using different kernels or different numerics seems like a rather haphazard way of addressing that.
Ultimately, it's really hard to, in any sort of analytical way, estimate what the forecast uncertainty is. Ultimately, because of the nonlinearity of the phenomena we're looking at, aside from saying that perturbations will grow rapidly, we can't say much more than that. So given, even if we knew with perfect precision what the initial condition uncertainty was in a given case, because we're so uncertain about the errors in a given case in the model itself, the best we can do is kind of a haphazard, very ad hoc way of trying to estimate what the forecast uncertainty is. So we just try to account for, all of the error sources that we can, which could be, we know the model numerics are a source of error, for example. Actually, that's actually a bad example because in general, at least with model numerics, more sophisticated numerics should in general give you better forecasts. But for example, our physics schemes, we have certain physics schemes that we know tend to perform better, but in a given scenario, they may perform horribly.
Yeah.
So short of actually using a variety of physics schemes, or at least taking that one physics scheme and perturbing it in some way, it's hard to get at what the resulting forecast uncertainty is.
Very interesting.
Kind of a related question. In your Kalman filters, how many how many unknown parameters you have, and do you calculate your propagation matrix from first principle, your covariance matrix from first principles, or you learn it from the data itself? So
the first question, how many tunable parameters? A lot.
Like 5 or 200?
Much closer to 5.
Okay.
And those the optimal values of those will again be case dependent. And we just, as a community, we kind of settle on accepted values that tend to work, across many cases. But again, the optimal values will vary from case to case. For as far as specifying the initial background error covariances, okay, so ultimately, once you have a background forecast, like when the new Z is run, it's initialized from an existing ensemble. So you can actually inherit the background error covariances from that pre-existing ensemble. But at ultimately, though, you have to start somewhere. I mean, that pre-existing ensemble had to be initialized in some way. And one way to do that, so you could initialize such an ensemble using fixed error covariances, for example, which is very suboptimal. But after you've cycled enough times, it no longer matters that you started from such poor initial background error covariances.
So along that line, I wanted to try to understand the going from the initial days model and then the predictions. That presumably started with some observables that you had that made it in, but then you're cycling without going back again to the full-on daily model that you started with, right?
Mm-hmm. Right.
Would there be benefit to being able to go back to something that was more updated at that scale that's only an hour old?
Well, actually, so the larger scale model is actually still impacting, in this case, the NUSI model, in that the background conditions, or the boundary conditions, the lateral boundary conditions for this nested NUSI
Still
domain
fluid.
are updated by the
Okay.
larger scale model.
Okay.
Yep.
Okay.
Yep.
And then one other question. It seems to me like, given what you said about the computational power you have available, if you have a ton of severe storm systems across the US, looks like it gets a little dicey for making, is there prioritization in where you're doing things at that point, or do you have enough power to handle 5, 6 massive multiple state storms?
Yeah, we don't. Right now, that slide I showed with approximately 1,000 kilometer wide domain, that's as big as we can do currently, at least with this Cray machine. Now, ultimately, this system or one like it will, be operationalized and will be running, in real time all the time, and maybe by that point it'll be running over the entire U.S. Although very likely not. Right now, I can't speak too much to the decision-making process that goes into determining where exactly to put the domain when there's multiple major severe weather threats, because I'm not part of those decisions. I actually am not involved in directly. I'm more of the kind of the basic research scientist in the group, so I'm not involved as much in running the NUSI. But the decision would largely be determined by where the highest risk is, according to the Storm Prediction Center.
Any other questions? Let's thank Corey again.